So don't worry if you found this one difficult, because it is. Let's go through it. We have a car travelling in a steady speed v in a circular path of radius r on a circular track banked at an angle. So as you can see, it's not just moving in a circle, but it's actually like on an angle. The car speed is such that there's no sideways frictional force between the tyres and the track. So we're used to understanding that the reason why a car would go around a corner is because of that friction. So it's telling you that friction doesn't exist. And in fact, you're going to have to think about what is the force that's actually keeping it in circular motion if friction's not there. We'll come to that in a second. Okay, so does the car have an acceleration? Well, this is, in fact, almost exactly the same as the previous question. In fact, the whole thing is just a very difficult version of the previous question with the weight on the string. So does the car have acceleration? Explain why or why not. Okay, so does it have an acceleration? Well, yes. The velocity is changing. Although the magnitude is constant, the direction changes. So that means that you do in fact have an acceleration towards the center of the circle. Okay, and that should be a complete answer. The car on the track is represented by a block, as we can see here. Draw a force diagram showing and labelling all the forces acting on the moving car. Now, all the forces makes it sound like there's hundreds of them, but actually there's only two. Okay, so on the one hand, we do have weight, which acts straight vertically down, and then we have the normal force, which happens as a reaction to the weight pushing down on the road. What's tricky about the normal force is that you have to remember that it's at 90 degrees to the surface, pushing straight up, perpendicular to the surface, like that. Okay, so those are our two forces, and just as a little bit of an extra thing for later, what we've got is the car is moving towards the centre, so we're still looking for a force towards the middle, right? So the resultant force is going to go that way. Now this is almost exactly the same as the previous question. We have a force inwards, F, which is caused by this force, okay, acting, a component of that force, N, acting in this direction. As you can see, F is at 90 degrees to mg, so the weight does not have any direct impact on the force. It does affect the normal, and the normal component then causes this circular motion due to F. Okay, so the next question. Is there a resultant force on the moving car? Yes. If you say yes, explain why and state the direction. If you say no, explain why not. In either case, refer to your force diagram. So what they're kind of asking for you indirectly is, where is this resultant force? And that's if you think there is one. Now, how do we know there is one? Because we're accelerating. We said in the previous question that the car was accelerating towards the center. Okay, and if it's accelerating, because acceleration is proportional to force, then there must also be a force towards the center. Okay, so part D is an unnecessarily complicated way of asking for a really simple thing. The track is banked at an angle of 17 degrees. So if we can imagine that this is down there, 17 degrees. And the circular path of the car has a radius of 30 meters. So now we know this is circular motion and there's a radius of 30 meters. Calculate the speed at which the car must travel in order that there be no sideways frictional force between the tyres and the track. Show all working. Now, because it's starting to talk about friction, then it seems to think that it's asking for something completely new, like what would make zero friction happen? It tells you that this entire arrangement here happens because there's no friction. So all it's asking you is, what is the velocity if this F is making it move in a circular motion? So using this force calculate V. Okay, so all we have to do is work out the value of the force. But the force is, as we said before, a component of the normal force. And the normal force can be found by looking at the component of the weight. Okay, so we'll do that in a step-by-step fashion now. Okay, so first we're going to find N. Okay, now we know that vertically we are in equilibrium because this car is not lifting off the road. So a certain component of the normal to the vertical will equal the weight. Now what would that be? We need to find what this angle is. And that angle there should be, well, you should be able to see that it's 17 degrees. Now, how can I convince you that it's 17 degrees if you can't see it yourselves straight away? Well, if this angle is 17, if you can imagine that line there, well, what you've got there is parallel situation. So if this is 17, then this is 17. Okay, so we've got 17 here. Now, keep going. If we have a perpendicular situation here, you can see that 17, well, that would be 90 minus 17. But we've also got a perpendicular situation here. So if this is 90 minus 17, then this must be 17, because that plus that equals 90. I hope that's clear. Okay, so now we know why this is 17 degrees. Let's do some resolving forces. So if we resolve vertically, okay, we know that N cosine of the angle, I'm just going to leave it like that for now because it's easier, less number crunching, equals mg down. Note, mental note, no numbers. They've given you very, very few numbers in this question. That's always a bad sign. That means that things are going to cancel. So let's leave everything in symbols until the end. So far we've got our resolving vertically n cosine. Okay, so n would be equal to mg cosine of the angle. Okay, so that's the first step. Now we need to try and figure out f. Now we know what n is now. It's that funny collection of symbols. Okay, so now let's see if we can come up with an expression for f. Now we know that this is 90 minus 17. Okay, so imagine a triangle like this. I'll even draw it in so you can see it. So imagine that line straight, and you've got a 90-degree angle like this. The value of f would be equal to n cosine 90 minus 17. Okay, so if n cosine 90 minus 17, then it's also equal to n sine 17. Okay, so resolving horizontally, f equals n sine of the angle. Okay, right, and that will be equal to mv squared over r. Okay, because remember, after all this, we've still got to find v. Okay, so what do we do now? Well, we need to substitute the value for n. We're going to substitute that into here. Okay, so let me clear a space so I can do that. Okay, so here we go. If we put mg cosine of the angle in here, we end up with mg cosine of the angle times sine of the angle equals mv squared over r. And we need to do a little bit of, cancelling and stuff. Let's have a look. We have mass on both sides, so looks like we didn't need to know the mass in the first place. And then we also have this fun sine of the angle over the cosine of the angle, which you might remember, hopefully from last year, that is equal to tan. So what we end up with is g tan of the angle. So that was a maths thing. If you remember, sine of the angle over cosine of the same angle equals tan. It's a neat little simplification trick. So back to this, equals v squared over r. So we could work out v squared easily by doing GR tan 17 degrees. So if we use the old mark, because this is an old paper, so it's 10 times 30 times tan 17 degrees. But now, this was back in the days where you could use 10, now you would have to use 9.81. So you'll get a slightly different answer. But anyway, you would give v squared, blah, 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 and you end up with v is approximately 9.86, factoring in the difference here. Okay, so you should get something very similar. Okay, that is a lot of work for 4 marks, but it is a tough question, I did say. So well done if you got it, and don't feel too bad if you didn't. It was a tough one.